All right, we can go ahead and get started. Um, as usual, shout out if you're having trouble hearing me or seeing me or anything like that. Um, thanks for um, joining again, everyone. Let me get going here. I'm going to share my screen and bring up the notes for today. All right, excellent. So again, as before, we're recording this webinar. Hopefully there won't be any interruptions, with my technical issues. And then this is going to be posted on the YouTube channel, so you guys can take a look at this in the future if you need to go back and review some things. As always, you're always free to email me with any issues. Better yet, put them in the issues section on the website. Haven't seen too many there, so hopefully that means people are doing okay with this stuff. But feel free to reach out with any problems, and I can usually work through them pretty easily. A couple of things that came up over the last week I want to mention. Number one, actually, this is something I encountered. I've been running this previously on the Ohio supercomputer cluster, and when I was trying to run the code in advance of today's session, ran into some difficulties, more or less building packages that I recommend that you use. So if anyone is using the OSC, you can let me know. We can discuss that offline. The bottom line, the problem is that OSC uses some very old software as sort of to compile packages, let's say, and so there's a way around that, but it's really inconvenient and not super clear. So if you're having trouble using the OSC, let me know and I can help you with that. For today, I'm running this on my directly on my Windows machine, so everything is basically been pre-built for Windows. So you shouldn't run into that same problem. So a couple of issues that came up last week using the Git commands script. People were running into issues where they would get an error when they tried to commit things, make a commit. And that happened in that particular case because nothing had been added. So you always have to remember to go through the flow of, you're going to make some changes to the project, okay, within that set of folders, right? Usually it's going to be to the R document in the R directory, and you got to save those changes. So if you don't save the changes, then Git doesn't know that anything's happened. All right. So you got to save the changes, number one, and then Git's going to recognize that something changed. And then you got to add it. What add does is it calculates exactly what all those changes are and puts them in an index. Okay. And the next thing you have to do is commit. And the commit is where you get to put a message around it and say, okay, this is what I accomplished with, all the changes since the last commit. So, and then you can push it to GitHub, and you can't go out of order and you can't go backwards. You got to go in that order. Otherwise it's not going to work. So just remember to run through those lines in a correct order. And if you haven't made any changes, then there's nothing to do. Another thing that came up is someone was using the set working directory command. Now, I strongly recommend against using that command. I know that shows up in people's scripts and on the internet and other things, and it's really problematic because what it's going to do, it's going to take you out of your project and put you into some other directory. And unless you immediately, when you're done doing what you intend to do, change the working directory back to where it was, and it's not always super clear how to do that, then you're going to be, all your subsequent sort of data is going to be written to that new working directory. All right, and that's almost never what you want to do. So instead, and usually this comes up when people are trying to import data or read in data, you're going to want to use a proper file path to do that instead. All right, instead of changing the working directory, you're going to use the whole file path. Now, I realize that folks, may have trouble figuring out exactly what the file path was, and there's a shortcut which I'll show you now, or let's say like a hint that you can use to determine exactly what file path, how to identify your file by the file path. And you might find this useful, actually. So there's this pane up here, there's different things you can select. Make sure you have the environment tab selected. And if you click on import, the first thing here is going to say from text, okay? It doesn't matter, really, I would just recommend using that from text. And then what you're going to do, you're going to find your data, okay? And, now this is like a normal sort of like file explorer, right? So you can, you should be familiar with that. So I'm just going to select this. It doesn't matter what it is, but, let's say that this is your data, then you click open, all right? And it doesn't matter what all this is either. So you can just click import, and that will actually import that data, those data into a new object with a name. So that's one way you can do it. Now that is, and you can say, all right, I'm done. Now the issue with that is like, that's not reproducible. That's not in a script. So like if you were to go back and do that again, then you like would have to find the same file. So that's a liability. So what you can actually do then is you can just, look at the console, and it very helpfully puts in the actual command that it used to do that. And therein lies the actual file path that you want to use. So then you could copy that and, paste that into, like, say, your script here, which, we're not going to use for today's lecture, but you could put it in your script, and then now it's tracked, and now forever, we know where that file came from. So that's a shortcut. But the bottom line is, don't ever use set working directory. And if it's, you think you're trying to, read in data, and you can't find the file path, that's a good shortcut to do it. Okay. So the theme, so we'll get on to the material for today. So the theme for today is, twofold. The first part is, ways to avoid errors and make your work, and sort of automate your work. All right. And we're going to do that through functions. Okay. So that's going to be the first half. And in the last half, we're going to talk about plotting. And plotting is obviously important because that's what's going to go in your paper or your thesis or whatever. So two major important techniques to go through today. So in terms of avoiding errors, we've already talked about a few methods. I mentioned the pipes last week. So pipes are nice because, it avoids you having to save a bunch of intermediate values if you're doing a string of manipulations or calculations on some data. So that's helpful. So that reduces the confusion, right? Another way you can do it, if there's really something that you have to save because the pipes just don't work for you, use a unique and informative name for variables. Don't name things like X or data or, value. I mean, these sorts of things are not good to be using sort of in an interactive way, because, you might confuse what X was or what value was. So use an informative name like experiment data with some date on the end of it. So another way to avoid errors is use functional programming techniques, which is, what we're going to talk about now. And then the last bit is to use processed, is to package your processed data. And we're going to talk about it at the end of the course. So these are really important things to make your work, more reproducible, for your future self. Let's say, like, you want to go back and figure out how you got a result from the beginning of your PhD. This is going to help you do that. Okay, so we're going to talk about functions now. So what is a function? A function is basically a list of commands or a miniature program that's going to usually take in some input and will usually produce some output. That's, they have to do one or the other in order to be a useful thing. Either produce input or take input, produce output, or do both. So it's like a little black box, I guess you can think of it that way. So functions are super useful in R. R is a functional programming language, meaning it's basically built to make using functions and defining functions very easy, and something you should be doing sort of like as second nature. Okay, so so let's just sort of talk about you know, how we're going to get started here. So let's go into the RStudio environment, and we're going to click on source, and that's going to load up our packages that we're going to use to start off today. Okay, and let's define a simple function. Okay, so in this case, you're going to use the word function to tell R, I'm going to make a new function. Okay, you're going to provide two, in this case, inputs. Okay, and inputs are, you know, generically named arguments. Okay, so we have argument 1 and argument 2. Inside is going to be some code. All right, that's the program that's going to run, and you can then use this word return to tell R to return a value. Okay, so very simple. So if I run this, what's going to happen? Well, nothing happened in terms of, so I'm going to get that out of there. So nothing happened in terms of the console, really. I mean, it didn't return any values. What it did was it defined the function. And here's this function, you know, in my global environment. And you can see it's named function name. All right, so that's not a great name. And argument 1 and argument 2 aren't great names, but you know, that's, you know, what you would replace for, you know, your custom functions, right? So, and then in order to make the function operate, what you're going to do is just something like this. So function name, and then supply the values for the arguments, you know, like shown, using an equal sign to assign those values to those arguments. And then it returns a result, 1 + 2 = 3. Okay, so that's the basics. That's very easy. And if you get nothing else out of this today, that's what you want to get out of the function part of this, and that's going to be a big help for you. So the next thing we wanted to talk about is a concept called scope. Okay, now scope is a very technical term, but it's something that is very basic and that you all already understand at some level. So, you know, when you're working on a document, say, you know, for your whatever project you're working on, you know, it can be a Word document or an Excel document, you save it with a name, right? And so that name is then stored by your computer. It's shown up in your file explorer, but it's attached to some value. And the value is the document that goes with that name. So that's a name value relationship, right? So, you know, and that's all that scope is. Scope is a set of name value relationships. Now, when you're talking about programming, you know, you have to maybe interact with it in a little finer detail. Okay, and you know, this is something that we've already encountered in what we're doing. So when we, you know, I think I showed you last week the conflicted package. All right. And we've loaded that, and it's been in the dependencies file. So we've loaded this conflicted package. And what is the purpose of this? And I briefly alluded to it, but what that package does is it handles conflicts in scope. Okay, so let's say you defined a function or let's say there was a function within a package with a name like function name or mean or something nondescript and common. Well, that may also live in another package. And so the computer has to have a way to figure out which one you mean when you call that function. Okay, so let me give you an example of this. So if I go back to this, I can show you that I've already attached this conflicted package. And let's say I want to run this command. Okay, so I'm going to say filter, and I want to filter that, and we'll say sil = 6. Okay, so it gave me an error. All right, so it gave me this error because it didn't know which filter I was referring to. All right, it's thinking I'm referring to a filter in the stats package, but I was actually referring to filter in a different package in the tidyverse package. So, so that's an example of R not understanding what I meant by this command. However, if I ran this, that's going to work. Okay, so that's how I sort of override that confusion. Okay, so that's an issue of scope. Okay, I can handle that up front by running this script here. So whenever I sit down to work, I'm going to run something like this to establish what I mean when I say filter. Okay, so that handles those conflicts in terms of scope, in terms of these functions. All right, so hopefully that's sort of clear to start off with. That's going to be an important, sort of fundamental. Okay, so so that's one way to think about scope, but that's purely in terms of functions. So scope also applies to data or values. Okay, and so let's say I created a value here in my global environment. Okay, so x equals 6. Okay, so that's living in a sort of a space. Okay, a memory space. And so how does R like understand what I mean when I call up x, and does it refer to some x in a different space, or how does that work? So oh, I can show you what R is actually going to do. So what I've done is I put X here in my what's called global environment, okay, or the workspace. That's essentially the same thing. And so the value of 6 has been assigned to the name of X within the global environment. Okay, so that's if I'm not working in a function, that's the first place where R is going to look for X when I call it up. All right, so that's the global environment. Now, let's say it doesn't find X there, or it doesn't find a function there, or it doesn't find some other value that I call up. It's going to look in these other namespaces or in these other scopes, these other environments. Those are all basically the same terms. It's going to look in these other ones to determine if it lies in there. And if it's not in any of those, it's not going to find it. Okay. And so what this concept is one of inheritance. Okay, so the global environment inherits all of these other environments from all the packages that I've attached to my session. Okay, so if I'm running a tidyverse function or a function from one of the, any of the hundreds of packages that you could use, it's going to look through all those and figure out if that sort of name is represented in those environments. And if it's not going to find it. Okay, but we're talking about making our own functions. So how does that work? Well, as it turns out, functions create their own special environment. And these environments are transient. They're only created as that function is running, and then they're destroyed. And this is a really powerful concept because it encapsulates everything that's going on within that function. And that is where you're going to protect yourself from generating errors. Okay, so if I say then create a value, assign a value to X within a function, when that function is operating, it's going to look first in that function's environment. Okay, and it's only going to use that one, and it's going to ignore X being defined in any of these other environments upstream. Okay, so that's how you're going to protect your operations from using the wrong values, which is going to lead to misleading errors. All right, so let me demonstrate some of this. So we're going to go here, and let's say we're going to define, I'm just going to get rid of X here because we don't need that. Let's say we're going to define a new function here called good sum. Okay, and this looks very similar to the function name argument that I put above. And you'll notice here that we have two arguments that good sum can take, 1 and 2. It's going to calculate a result, and it's going to return that result. Okay. So I've now saved the function in my global environment. Okay. So it's in now living in this guy here. All right. And now I can call it, and R is going to look first in the global environment to figure out what good sum is. It's going to run that code, and it's going to produce a result. All right, so that result is 3. So that is pretty simple, right? So let me give you an example of inheritance. Okay, so as I mentioned, when that function is operating, it creates its own little mini environment. Now, if it needs something that isn't in that environment, it's going to go looking in these higher environments. So this will be created. If it doesn't have what it needs, it's going to go looking in the global environment. And that is something that you usually want to consciously avoid. Okay. And the reason is you might have something named that conflicts with what you're calling in that function, or something that you hadn't intended. And that could bring a value in which might cause an error, or even worse, would cause an incorrect result that doesn't cause an error. Okay, so in this case, the bad sum, you'll see, well, it's only got the second argument there, but it's actually going to need 2 arguments. So there's an argument that's not called directly by the function. All right, and so that is what these arguments are, what create that environment for the function. And so you'll notice that that's not in one of the listed arguments here. So it's going to go looking for that outside of the environment. All right, so we'll do bad sum. Okay, so now that's been defined. Now, as I said, it's going to looking for addend1, but I haven't provided it, so that's going to return an error, right? So object addend1 is not found. Okay, so what I can do to sort of like put a band-aid on this and fix it is generate addend1. It's now living in my global environment, as you can see here. And now bad sum is going to work. Okay, so 2 + 2 = 4. All right, but let's say I had changed addend1 at some other point in a different section of my code. Bad sum is going to give me a different result, so that's not good. And the other point is, I've now named addend1 here in my global environment, and there it lives. But now if I call addend1 for good sum, and you remember that is used here in the good sum as well. Okay, if I call it here, it's this value here is going to override what's in my global environment. So 3 + 2 = 5, and we don't use this 2 value here. So as much as you possibly can, all of the inputs to your function, you want to put them in this function call here as arguments. Okay, hopefully that's clear. And if there's any questions, I think this is stuff that is pretty easy conceptually to sort of get your head around, but in terms of how to do it in practice, it can be a little bit challenging. So if you have any questions about that, definitely let me know. Okay, so let's go through a few more things. So you can choose to return, you might calculate many things within a function. Okay, and maybe you want to return one thing, but maybe you want to return like more than one thing, like several plots, or a plot in a table, or a plot and some values. Well, R is only going to let you return one item from a function. Okay, so the way around that is to put all those things into a list. We talked about lists last week, and then just return the list. All right, so here we're going to calculate the mean and the median. We're going to put those into a list, and we're going to put the names on the values of the list. That's in case we want to come back in the future and figure out what these things actually are. And then we're going to return the list. Okay, so there's 2 averages, and we can run 2 averages over this vector of values here, and we get this list as a result. Okay, the mean is 3.1, the median is 3. Okay, so very useful technique to have there. Okay, so next we want to talk about conditionals. All right, so we introduced sort of logical tests last week, You know, we showed some very sort of trivial examples like 1 equals 2 is false, right? So, but you might have some more complicated things, like you might want to supply as an input to your function a list of values, and then, you know, depending upon what each of those values are, you want to do one thing or maybe do a different thing. And so conditionals are really useful to automate and to handle different cases when you're building your functions. Okay, so I want to show you, you know, how we're going to do that. Okay, and here's an example of where it could be useful, but you can think of many, many other sort of less trivial examples. So, you know, we can try and, you know, make this function that does a division operation. Okay, so obviously what happens when you divide by 0, it's undefined, and in this case it returns an infinite value, which is, you know, not useful. Okay, so that's what we can call an unsafe divide. But we can, you know, because we know that you can't divide by 0, we can actually watch out for that and fix that. Okay, so, you know, we can put something like this, an if-else statement in our function. Okay, so it's going to, you know, look at x and y. It's going to encounter this and say if x, you know, so if y equals 0, okay, yeah, well, then it's going to return you can't divide by 0. Otherwise, it's going to return the value. All right. In all other cases, that should be defined. So, so that should work. All right. So let's run that again. Okay. And so now we try and divide by 0. We get the helpful message you can't divide by 0. All right. So, you know, that's going to be something that, you know, as you get beyond sort of the trivial functions and what you're doing, it's going to be, you know, more and more useful. All right. All right. So next I want to talk about mapping. Okay. So mapping is a functional programming technique, and the basic concept is just as I say here. You're going to apply your functions to a vector or a list of values. Okay, so let's say you've defined a function that's going to do something, but you might want to run that function on multiple values of input. Okay, this happens like all the time. So let's say you wanted to make a plot of expression of a gene, or you wanted to make a, and you want to do like 100 genes, or you wanted to even something as simple as 3 repeats of an experiment. You wanted to calculate a table from the 3 repeats of experiment. Well, you could use this mapping concept to apply a function that generates that table to the 3 different pieces of data, the 3 different repeats, to all the genes in your gene list, these sorts of things. So really, you know, like there's an endless ways that this becomes useful. And the end result is that you get a list of results put together in a single object, which is very convenient. And you have like no duplication in your code. So you don't want to be, you know, repeating function calls or repeating lots of detailed code because, you know, it's very easy to mess that up. All right, so map is, if you can think in terms of applying a function that you've built to a list or a vector, you're going to be in really good shape. All right, so how is this constructed? So this map function, this actually comes out of the purr package, P-U-R-R-R. Okay, so we can just put that in there for you guys. So it comes out of that package. You're going to supply 2 things. Okay, one is going to be either a list or a vector. It will use either. In this case, the values 1, 2, and 3. And you're going to then supply a function. Okay, in this case, I've done a little shorthand here with this backslash. You know, that's sort of a short, like I said, a shorthand that I often use, but it's the same thing as function. Okay, you can also put that there, doesn't matter. So backslash in R is the same as the word function. Okay, so what happens when we do that? Well, we're going to apply this function, all right, which is just calculating x plus 1 to each element of that vector, and it's going to return it as a list. Okay. Yeah. All right. So we're starting with 1, 2, and 3. We're going to get 2, 3, and 4. Great. All right. So super simple, but useful. All right. Well, maybe we don't want to list. Okay. So you can imagine a lot of scenarios where you wouldn't. Maybe you just want to return that as a vector. All right. It turns out there's a lot easier ways to go about this particular what we're doing here, but this is just an example. But there are variants on this mapping function that you can use that will return the data in a different form. Okay, so if your data can be turned into a numeric vector, then you can use this function here, and it will automatically take that list and crunch it back down into a vector. All right. So map DBL or double will give you this nice numeric vector out. Okay. So if you go to the per cheat sheet, cheat sheets are always good. Just Google per cheat sheet. That will give you all the different sort of variants on that theme. Okay. All right. Here's another sort of more useful thing called map2. This instead of taking one vector input, it's going to iterate over 2 vectors basically in parallel. So it's going to take x from the first vector, first element of x, first element of y, and then feed those into the function. Okay, and here your function has to be of x and y. All right, so you'll see what this does. Okay, so it returns a list where we've now said, all right, so the first result is 2, the second result is 3, the final result is 4. All right, and that's obviously the text is coming from y and the numbers are coming from x. So also very useful. You can extend this to an arbitrary number of values, basically, or a number of variables, let's say, by using this pmap. All right, and so pmap, instead of .x, .y, you're going to supply a .l. .l is going to be a list. In this case, it has to be a list. But the elements themselves can be vectors. All right, so the name of this is going to be x. It's going to be this vector we were working with. This is going to be your beginning text, and then your end text is going to be these guys here. And all these things that you name here have to show up in here. Okay. And we're going to say, result is that, and we're going to return, we're going to paste the beginning, the result, and the ending, and that should give us something like this. Okay. One thing that does come up that I should have included here, but let me just include it now, is that it's often, you want to have something that's fixed as an input. Okay, so let's say there was something that you didn't want to iterate over, but you just wanted to have that, apply to all the values. Okay, so you can do it like this. So you actually don't put it in this list thing here. You're going to put it in the function call, and the way you do that is, we'll say final text equals I don't know, I want to say, let's say is a period. Okay, so we'll put a period on the end of this. And then, so instead of this return, we're going to return the end text and the final text. Okay. All right, so now if we run it, we got the period on there. Okay, so that's how you put like a fixed input that you don't want to iterate over with your mapping. Okay, so that's pmap. All right, that's all I had on functional programming. I think that's going to take you a long way if you can sort of understand those concepts: scope, building functions, and applying functions. You'll be in good shape. All right, so we're going to switch gears now, and we're going to talk about plotting, which is something that you all should be interested in doing to make figures for your paper. So we'll just start here with some data. Now you're familiar with this data. This comes from like a built-in data set, and we worked with this before. But here you go. So this is some flower petals, and they've done some measurements on there, and there's some species on there. Okay, so that's good. Now you're going to want to use ggplot for 95% of the figures that you're going to make. are they have the easiest interface in terms of building the code, the way that you want to make the figure look. In the end, the figures look the best. It can cover just about everything except for, let's say, heat maps, and some of the basic plotting functions involved with modeling are a little bit not so good in ggplot. But outside of that, everything you're going to want to do is within ggplot. All right, so ggplot's a package. It's in the tidyverse, so you don't have to, if you attach the tidyverse packages, you'll get it in there. Now, the way ggplot works is it gives you a base framework for the plot, and then you add layers on top of it. Okay, the base framework is really just like not going to return anything. So if I run this, I have to supply the data into this data argument, and I have to supply the mapping. All right, and so what mapping is, it's mapping your data to visual dimensions that you're going to represent in your figure. Okay, so this is just the framework. It's not going to do anything. I mean, it didn't plot any data, let's say. It did set up the framework for the plot. So what is this showing? Well, it's it's got species on the x-axis. Okay, so that's good. That makes sense. And it's got this length on the y-axis. So that's pretty clear. All right. Well, x and y, those are two useful dimensions. But there's a lot of other dimensions that we're going to explore. Size, shade, color, these sorts of things can be used as different dimensions to show highly dimensional data, which is something we're going to need to deal with. All right, so layers are added using this plus sign here. The most basic layer is like a geom. So a geom is like a visual representation of your data. As I mentioned, all the data is in here in this framework because it's not being shown. So we have to tell ggplot to show it using a function, and these functions are always geoms. All right, so you can use you can look up different geoms to use for categorical data, like the species. I think geom jitter is generally the best one to use. And I'll show you what that looks like. Okay, so that was very easy. What it's done is it's showing every point here from our data. It's added a little bit of random noise to the values in order to reduce overplotting. All right, so obviously all the values here are the same, like this versicolor, like all these are versicolor, but it spread them out so you can see them. And that's what jitter does. If we change this to geom point, it's going to be you'll see what I mean. All right, so everything's stacked up there, and that's actually not super helpful. So what we can do is we'll just go back to the jitter version, which is, I think, more helpful. Okay, so that's good. So we can do some more things with this. One thing that we can do is we can use the color of these points to indicate more information. All right. Now, may or may not be a good idea or necessary to do that. Sometimes too much color can be distracting and can take away. But sometimes color is good, and even if you don't need it in an isolated plot, it might help connect multiple plots or multiple figures in your paper. So being able to assign color to your points is a useful thing to do in any event. The other thing we can do is within this geom jitter function, we can assign common things that are going to apply to all of the data or all of the points, like the shape, the size, the transparency, these sorts of things. So if you put something here in this mapping, these aesthetics are going to be mapped to your data. All right, so that makes sense. These things down here are going to apply across the board. All right, so let's see how that looks. Okay, good. So we're back to the jitter. We've now got different colors for the different species. The we've now generated a legend, which is helpful. And we've made the shapes look the way we want. We've changed the size, we made them a little bit transparent, and we've made it, this 21 shape, which is a nice circle. Okay. Okay, so that's good. So, you're always going to want to, when you're plotting data like this, where you've measured a continuous variable like length, and you've got it broken down into categories, you're going to want to put in some measure of central tendency, like a mean or a median, and you want to put some error in there. All right, so error bars basically. All right, and the way you do that is through these stat functions. Now these are a little bit, let's say, like not easy to work with, because you have to know exactly how to construct these. So my recommendation is to take something that works, like this is going to work, and then just copy it. All right, and next time you're going to make a plot, say, oh, how do I do that? Go back to this script and say, all right, that's how I want to do it. And then as you sort of explore the different variations on this, and there's options, you can make different geoms, you make it different colors, etc. Then you'll find what you like for your figure, and then you can just use that. All right, so we've done that now. Okay, so that's good. It's added the mean here in a thick bar, and it's got the standard error. We could also do standard deviation if we wanted to do that. Oh, actually, that's not available. Okay. Well, we'll have to see here. Mean. Is that it? Let's see. Nope. All right. Well, so let's go with the mean and standard error. So as you can see, there's a little bit tricky to work with. I usually just use mean and standard error, but you can actually define that separately, and I have some other functions that can do that, but it's not really super important at this point. Okay, so so that's good, but you also want to put in like statistical testing, right? So like you want to do a t-test or a Wilcox test between these groups. All right, that makes sense. So this package here, ggplot, is pretty convenient. I mean, it's not like essential, but it really makes these error bars and not error bars, but little stars for the significance that everyone wants to put in their papers. It makes that pretty easy to apply. And so what we'll do is we'll just attach that package. We have the same code up here. All we're doing is adding on this bit down here. All right, what this is doing, this is actually pretty easy to interpret. So it's gonna compare the means of our groups. All right, it's going to use the t-test to do it. It's going to use this form of label, which is going to produce the stars. So there's two options there, which you can look into, but that's going to give you the stars, and it's going to do comparisons. All right, so we have 3 groups, so I have to, you can only do 2 groups for a t-test, right? So you have to tell it which groups you're going to compare. So this will do all 3 of these comparisons, all the different pairwise comparisons. All right, so let's run that. All right, cool. So it's given us these, little error bars and stars and whatnot. So that looks pretty good. So let's see here, Brad. When trying to perform the comparisons, I keep getting this error. Error in stat compare means. Could not find the function stat compare means. I did load ggplot. Okay, well, I don't actually have a quick answer to that. It should be working. If people are not able to get this ggplot thing to work, let me know. But that is a useful thing to do in general. So sorry, I can't answer that right now. All right, so let's do this. Change the colors. All right, well, you can see we've got these sort of default colors here. Right? So like this sort of salmon colored and green and then blue. And maybe we don't like that. So, the way you tell R to apply different colors to different visual aesthetics, like a shape, is with the scale command. Okay, so scales map values, so color values to aesthetics. All right, and so one like very convenient function to do this is the color brewer package. This is if you Google R color brewer, let me show you this. R color brewer. This gives you a lot of nice options that are, colorblind safe. They look good. They're easy to tell apart. So that's sort of, where I turn to first for a good scale. But that's where these values are coming from. And this is going to pick that dark 2 palette, and it's going to apply that palette to the values that we've got for the fill aesthetic and the color aesthetic. So let me show you what that looks like. All right, so it's got those 3 values now. We've got this sort of darker, different colors, basically. There are a lot of different palettes that you can choose from. You can construct your own palettes using Scale Fill Manual. Okay, I'll show you that. Manual. Okay, so values. We'll put in 3 colors here. So red, blue, green. Okay. Show you how that works. So if you didn't like any of those options, or you had to pick something else, you could do that. All right, so now we've got red, blue, and green. All right, that's good. So you can pick basically any color that's available there. You can use hex values. All right, you want to use a hex value. Do that. So FF0. All right, there's some different hex colors. Oops. Right, so now you got like red, yellow, and like cyan. Okay, so that's good. And then you can actually also explicitly assign these values. Okay. Oh, actually, I do have some code down here for that. Yeah, so let's go down here. So here I've done that for you already. Sorry, I forgot I had that. You use this Scale Fill Manual, and then you can do a named vector. All right, so this will assign the the Setosa value to red, this one to green, and this one to blue. All right, so that's very useful to do as well. Let's say you wanted to have certain colors apply to certain values, you can do that. All right, so now we've got the red, green, and blue back. Okay. All right, so so that's good. Now the next thing is the theme. All right, so this is sort of a base theme that is offered by ggplot. It's sort of like weird gray, and I usually will never use that because I don't like it. So this package here, cowplot, has a lot of nice sort of helper aesthetic functions for you. So we're going to attach cowplot, and then we're going to apply here. We're going to apply the cowplot theme, and you'll see what that looks like. Okay, so you run that, and so okay, that actually looks like something you might start to see in a paper, right? So that's good. Yeah, so the other thing we've done here, I wanted to mention, is that we've gotten rid of the legend in this. So that's how you get rid of the legend. Make the legend position to none. The legend goes away because we don't really need the legend here. The colors are just for like visual appeal and maybe to connect to some other figure that we've got in another plot. So, okay, so last couple of things here. We talked last week about doing some statistical testing, so I want to show you how to do that because that's obviously important. It's going to go along with your plotting. All right, so this is a base function that's going to calculate the t-test of some data. All right, and what is the data? The data are going to be this here. So it's going to be the Setosa values from this data set. And so what that will do is that set of commands will make this big vector here of numbers. This one will likewise produce a vector of numbers, and it's going to calculate the t-test results between those two vectors. Okay, and so this is a lot of text coming out of here, and if you like sort of hunt through it, you might find that the p-value is that there. So that's useful, I guess. You know, but it is a lot of text, and maybe that's not like the most helpful format for what you want to do. So there is this package here, which is very helpful, called rstatistics, and doesn't do anything different, but it sort of wraps up a lot of different calculations and produces them in a way that is more convenient for you. And so here, this function from that package, get summary stats, will like basically take groups that you've defined. So let's say I want to group these data by species, or you could group, let's say, by by experimental condition, or in which case it would be control and experimental, that sort of thing, and it will calculate for you the all these useful things that you're going to want to report in your paper: the min, max, median, et cetera, et cetera. So that is super useful to do. The other thing you can do is you can actually do the comparisons using this package, right? And so what we've done here is using this t-test function, and there's a bunch of other ones. There's Wilcox, there's a ton of other ones, and they're all operating the same way. It does request or require that you put basically input the data in this sort of unfamiliar format. The little tilde is sort of it's called a formula format. All this means, if you translate this into like English, this would be calculating the t-test on the length, sepal length data as a function of species. Okay, so and then if you look down here, it's going to do all of the pairwise comparisons between the two values. Okay, so you can see there's pair 1, there's pair 2, there's pair 3, and it calculates all of the p-values. It does a multiple comparisons correction, and gives you all those values. Okay, so that's super useful as well. All right, so I think that's going to be it for today. Hopefully, that's going to be something that you guys can go through over the next week. As before, let me know if you've got any questions or any issues. I will try and work with everyone. Let me know if you have any problems loading these packages or getting them installed or anything, because that can be very frustrating. All right, folks. Well, thanks for joining. I don't see any other questions. I'm just checking the chat and the Q&A here. It all looks like everything is pretty clear. So have a good week, and we'll see you next week. Thanks.